Thank you for taking a few minutes to watch this video. This is a video on Precalculus review for a Calculus 1 student. In this video, I'm going to do a few specific types of problems, the composition of functions, some problems with radian and degree measurements, evaluating a difference quotient, and then stating the domain of a function in interval notation. Before we get started, let me encourage you with this note from Nibbler Pie. Nibbler Pie is a math expert. She's a math expert, of course, because she was born on 3/14 Pi Day, and she knows that you can do this. So make sure that by the end of the time that you're working with these types of problems that you feel confident in your ability to do each of these types of problems on your own. Here's how I'd encourage you to do that. You could take these different problems that we've got lined out, and you could try each one of them on your own. You could try each one of them again later without any notes. And if you can do these problems without any notes eventually, then that's how you know that you're on your way to being ready. If you want to really be certain you're ready, then what you'll do is find some additional examples that are similar but maybe a little different, and check that you could do those examples also. Just watching this video, you're not going to gain the skills and knowledge that you need. So I really want to encourage you to practice, practice, practice. Math is not a spectator sport. It's an action sport. You've got to get in, and you can't just watch soccer and become an expert soccer player, right? In the same way, you can't just watch someone else do math and then become an expert in math yourself. So you've got to jump in and try these problems. Let's start with this composition of functions. When I see this f of g of x, I read it f of g of x, and I could write it f of g of x like this. I'm going to color code this g function. And what this means is we're going to take our f function, the x squared plus 3, and we're going to replace the x with the 2x minus 1. We're going to replace x with g of x. We're going to replace x with 2x minus 1. Let's see what that would look like. So actually, I could say I've evaluated the composition of function. This 2x minus 1 squared plus 3 is correctly done, but I now want to simplify it, right? And that's where the algebra comes in. When I simplify this, I want to use some patterns. So I'm going to, instead of foiling 2x times 2x, 2x times negative 1, negative 1 times 2x, negative 1 times negative 1. I don't have time for all of that. So I'm going to use this pattern and say that 2x squared is 4x squared. 2x times negative 1 is negative 2x, and if I double that, I get 4x. Negative 1 times negative 1 is positive 1. And, I should have kept that all color-coded. Let me highlight it blue so that we keep this as our 2x minus 1 squared. And then what I'm going to do outside of that is say plus 3. I'm going to carry down that plus 3. So we have 4x squared minus 4x plus 1 plus 3. If you don't know where I get that 4x squared minus 4x plus 1, then try this algebra again, maybe with FOIL. But once I combine those like terms, the final answer, 1 plus 3, gives me 4x squared minus 4x plus 4. Let's move on to h of z. H of z. So we've got h of z of x. So I'm going to take this z. Oh, you know what? It looks like I didn't write the z. Or did I? I just called it something different. Let me fix that. I didn't write the h or the z. Let me write these. Z of x should have been square root of 3 minus x. And h of x was given as x cubed plus 4. If we're given h of x is x cubed plus 4, and z of x is the square root of 3 minus x, again, all I'm going to do is go into the h function, cube the x, and add the 4, but I'm going to replace the x with our z, square root of 3 minus x. And that's it. Though you, as a calculus student, should be able to do some algebra simplifying of this. A few ways you could simplify this. The piece you want to catch is that the square root cubed isn't simplified. A square root cubed, if it's a square root, let me write this out so that I'm not losing anyone here. I could say it's 3 minus x, square root of 3 minus x, square root of 3 minus x, all of that, right? And then don't lose our plus 4 hanging off the end here. But you see, I could take 2 of these square roots and pull it out. A number of students have done that on the quiz we did, but then left off those parentheses. Another way we could simplify this, you really could go even further. You could distribute the 3, distribute the negative x, so I don't think that's necessary. And another way that you could simplify this is recognize that this 3 minus x is, when it's square rooted, it's to the 1/2, and then when we cube it, you get 3/2. So any of those would have been okay, and you could maybe even argue that this is simplified. But watch your algebra. If you do simplify it in other ways, make sure you're doing the algebra carefully. But that's the general idea for the composition. Let's look at an example with degree and radian measurement. And to start with, keep in mind, what does it mean? If I have a circle with a radius of 1, so the radius is 1, the diameter is 2, then what I could say is that the circumference of that circle is 2 pi times the radius, or 2 pi, right? If I went all the way around. So what that is reminding me of is that if I went all the way around the circle in degree measurement, it'd be 360 degrees. And this reminder that 360 degrees is the same thing as 2 pi radians. And how can I remember that 360 is equivalent to 2 pi radians? If I do the circumference of a unit circle, the circumference is 2 pi, and so that alerts me that the radian measurement going all the way around the circle, which is 360 degrees, the radian measurement is 2 pi radians. So all this to give me that pi radians is equivalent to 180 degrees. What I can do to use unit fractions to do this is say I have 250 degrees and start by writing that over 1. And then what I can do is multiply that by 180 degrees under pi. Under pi radians, right? Because pi radians over 180 degrees is a fancy way of saying 1. So I can use a unit multiplier, pi radians over 180 degrees, to multiply times the 250 degrees. And when I multiply by that 1, I don't change the value of the function, or the expression. I don't change its value because I'm multiplying by 1. So if I work this out, I have 250 pi over 180. The degrees divides out, and I'm left with radians. So there it is, but it's not simplified, is it? I should recognize really easily that I could divide both of those by 10. 250 pi divided by 10 is 25. 180 divided by 10 is 18. So I get 25 pi over 18. You could also write that, I've seen it written like this, if it's really clear that the pi is being multiplied by the whole thing. But if you write a little bit messy, I'd encourage you to write it really clearly so that that pi is on the numerator. But that's how many radians it is. Watch out for this 3 radians. I think what throws students off is thinking, well, wait, there's no pi in there. I've got to have pi. Well, you don't always have to have a pi when you're doing when you're looking at a radian measurement. So if I just apply the process of multiplying 3 radians over 1 times pi radians under 180 degrees, and remember why I put the radians in the denominator, so that they divide out, right? Then what do I have? I've got 3 times 180 over pi. 3 times 180 over pi. And that's how many degrees it is. Now, if I multiply that 3 times 180, I'd get 540. So I'd have 540 over pi degrees. Don't be thrown off thinking that, oh, if it's got a pi in it, it has to be radians. I can't have a degree measurement with a pi. Well, pi is just a number. Pi is just a constant. It's approximately 3.14, but it's just a constant. So get used to seeing that pi often. Let's look at the difference quotient. I showed in previous videos and in class a method that I like to use for this to keep it really lined up easily. I'm going to evaluate this f of x plus h. And to do that, I take the 2 plus 5 times x plus h minus x plus h squared. So I'm replacing the x with x plus h, right? Replace all the x's with x plus h. So we have 2 plus 5 times x plus h minus x plus h squared. You've got to get to where you can do that distributing and multiplying out easily but accurately every time. I'm going to distribute the 5. I've got to be really careful with this x plus h squared. So this x plus h squared, by using the pattern, it's x squared plus 2xh plus h squared. I've done that by knowing that pattern. You could try foiling it out. But what I'm going to be really, really thoughtful of here, and I'm going to highlight it here, is that I've got to subtract all of those, right? So here's what that's going to look like when I write it out. It'll be the opposite, opposite, and opposite. So the opposite of x squared minus x squared, the opposite of 2xh, so minus 2xh, and the opposite of h squared, so minus h squared. Don't lose those negatives there. And where did they come from? Because this negative has to go to everything, right? And it's this negative right here. Minus x squared. It makes it a little tricky, but it's doable. Let's look now at continuing this. We've got our f of x plus h. And what we want to do with that is subtract f of x. So I'm going to do the subtract f of x below. Watch how nicely this lines up if I do it correctly. Subtract f of x, so subtract 2, subtract 5x, subtract the opposite of x squared. So that's really adding an x squared, right? And when I subtract these, if I've done it carefully, I'm going to see a lot of things cancel out. This 2 minus 2 cancels out. 5x minus 5x cancels out. The opposite of x squared plus x squared cancels out. So I get some zeros here. And then I'm just going to carry down what was left. What was left over? I have this 5h, negative 2xh, negative or minus the h squared. So now I've got my f of x plus h minus f of x, that's the numerator up here in the difference quotient. And then if I divide all of this by h, what I'm doing is dividing each of the three pieces by h, right? If I play it out correctly, I get a nice, neat 5 minus 2x minus h squared over h is h. 5 minus 2x minus h should be the final result when I evaluate that. Look at that process again. Do you follow how this might help you? Now, if you're getting this correct every time because you've got really good algebra skills under your belts, then go ahead and continue doing this problem whatever way works best for you. But if you're not getting this every time, I'd really encourage you to use this process. To do the numerator, 5 or f of x plus h minus f of x, I'm going to write them above each other. So I've got my f of x plus h here, and then I'm going to do subtract f of x here, and it lines up so nicely. I can see clearly what cancels out. 2 minus 2, 5x minus 5x, the opposite of x squared plus x squared. I get these nice zeros, right? And so then just carrying down what I've got left, 5h minus 2xh minus h squared, divide each of those by h, and I get my end result. Let's look at another example, finding the domain. Right off the bat, we have a really easy one because this is a polynomial. There are no issues with the domain. It's all real numbers. And in interval notation, we say all real numbers by looking at the number line and saying anything on the number line goes. Anything from negative infinity up to infinity. So I'd write it parenthesis, negative infinity, comma, infinity, parenthesis. With the number 7, we're not quite as lucky as that. There is one problem with the domain. I've got to make certain that I don't get a 0 in the denominator. So I've got to say that 3x minus 7 can't be 0, which means 3x can't be positive 7, which means x can't be 7/3. Now, how do I note that in interval notation? If I put this on a number line, I might see it like this, that I can have anything except the 7/3, right? The way you transfer that over to interval notation is to say we're going from negative infinity up to 7/3, but then we're going to exclude the 7/3. So I'm going to put a parenthesis there to show I've got to leave the 7/3 out. Or 7/3 to infinity. The negative infinity, infinity, of course, always have parenthesis, not bracket, because you don't ever actually get to infinity. It doesn't ever equal infinity. Similar example here with number 8, except that this 2 plus 5x, it can be 0. It just can't be negative. So I'm going to say this radicand, the piece inside the radical, the 2 plus 5x has to be greater or equal to 0. So we get 5x greater than or equal to negative 2, x is greater than or equal to negative 2/5. If you picture this on the number line, here's a negative 2/5. I can equal negative 2/5, so I'm going to have a closed circle or have anything that's greater than that, up to infinity, right? So in interval notation, I'd say include negative 2/5. So I've got a bracket and go up to infinity. That's just a notation for interval notation. And then last but not least, number 9 here, if we're looking at rational function, what we're going to be concerned with is when is the denominator equal to 0. Many students do a good job of this, factoring that denominator. When you look at the numerator, you want to see if there's anything that divides out, and there actually isn't anything that divides out. But let me tell you that even if something divided out, so let me say that, let's say that, let me not erase it. Let me do this. What if the top was x plus 5? Yeah, sure, you could divide that x plus 5 over x plus 5 to divide that out. But let me make sure you understand this. That x plus 5 in that denominator still tells us that x can't be negative 5. So even if you could factor, you'd want to still be keeping the denominator non-zero. So let me back out of some of that pink stuff that doesn't apply directly. So this f of x equals something over x plus 2 times x plus 5, what we're going to say is that x plus 2 can't be 0, which means x can't be negative 2. X plus 5 can't be 0, which means x can't be negative 5. And watch what happens if I put that on a number line. So how do you translate this over to interval notation? We're saying I can pick anything on this number line except the negative 5 and the negative 2. So I could go from negative infinity up to negative 5 to negative 2, or negative 2 up to infinity. What does that look like when I write it in interval notation? You go ahead and write it. Write it out. See if you've got it. Maybe pause the video to see if you've got it correct. Here's what you should have had. Negative infinity to negative 5, or, and we're going to exclude that negative 5, or negative 5 to negative 2, excluding the negative 2, so a parenthesis, not a bracket, or negative 2 to infinity. And that's what it would look like in interval notation. Well, that wraps up these examples. I hope that you found these helpful. Reach out to me through email or visit with me in class or visit me outside of class during office hours. Send me an email if you want to try to connect, and I would be happy to help you further. But thanks for the work you're doing. Keep plugging away at these problems. And again, the best way to get to where you can do this yourself is to practice. Practice these problems. Maybe go back to the beginning and try each problem. Pause the video and do it on your own. See if you can do this without notes. And that's when you'll know that you're ready to move on.